Welcome learners to lesson number 2 of the topic Light and Lenses. Light and lenses. And this happens to be lesson number 2. In lesson number 1, we looked at the definition of a lens. We looked at the definition of a lens, in which we said that a lens is a material carefully molded so as to refract light. So it's a material that is carefully molded or carefully shaped in order to refract light. And we noted that lenses of all types are made up of glass. They may be made up of a transparent plastic, and they can also be made of a material or type of glass known as Perspex. Aside from that, we looked at different types of lenses. Different types of lenses. We said there are two main types of lenses, namely convex and concave lenses. Remember that convex lenses are also called converging lenses, while concave lenses are also called diverging lenses. All right. So in as far as this topic is concerned, we are going, as you will notice, we are going to dwell much on the operation of a convex lens. And in very rare cases, shall we talk about convex lenses. So lenses are in use in many devices, as we noted in the introduction, that lenses are found in cameras, they are found in telescopes, lenses are found in instruments such as slide projectors, as well as your own eyes. An eye isn't much use without a lens. So in lesson 2, we go further than where we stopped last time by looking at the effect of a lens on the parallel rays of light. What happens to rays of light as they fall on a lens, be it a convex lens or diverging lens? Okay, what we mean by this is that suppose we have a lens which is convex in nature, and then we have rays of light that are parallel, originating from somewhere and falling on a convex lens. What is going to happen to the rays of light as they emanate or exit the lens? So this is a lens. This is a lens, and these are rays of light which are coming from somewhere, from a source, from the source of light. So when they hit the lens, what is going to happen to them? That's what we mean by effect of lenses on parallel rays of light. That's basically what we are talking about. So through many experiments that have been carried out on the study of light, a lens depends on the principle of refraction of light. So we are saying a lens, the principle on which a lens works is refraction. In Form 1, rather Form 2 of your JC Physics, you learned that when a ray of light travels through air, so this is air, let's say, and then passes through a material with a greater optic density, like a lens. So this is a lens. The ray of light will not continue to travel in a straight line like that. No. Instead, it is going to bend. The ray is going to bend. So the ray of light, upon reaching the lens, it's going to bend. So this bending of light is what is called the refraction. So what are we saying? We are saying that when the ray of light strikes a lens, it is going to bend. So the bending takes place at the boundary between air and the lens. Remember that lens is made of glass. So by nature, glass has greater optic density than air. So at the boundary between air and the glass, which is here, the ray of light is going to bend. So the bending of light, as you defined in Form 2, is called refraction. So we are saying a lens relies on the principle of refraction of light. In other words, lenses cause light rays to refract or to bend. So this being the case, therefore, when parallel rays of light are directed towards the lens, the rays will be refracted either by being converged or by being diverged. Take note. So you're saying a lens can cause rays of light to converge or to diverge. What do we mean? Suppose we have a lens like this, and the rays which are parallel to each other fall on the lens like that. So as they get out of the lens, there is going to be refraction, bending. So any other ray which is not passing through the center of the lens is going to bend. So this one will bend like that. This one will bend like that, so that they cross at a common point. We are going to name this point later on. So the meeting of rays of light after refraction as they get out of the lens is what is called the converge. To converge simply means to come together, to meet together. So in relation to rays of light, the rays of light have converged here. They have converged there. That's called the point of convergence. Point of convergence. But in some circumstances, some lenses, such as the diverging lens, instead of bringing rays of light to a common point, the rays spread far apart or in different directions. Let's say that we have this ray of light which is passing through the center, and we have this one which is parallel to the one passing through the center, and another one also like this. For a diverging lens, the ray of light, upon reaching the lens, is going to be spread apart like this. So this will go this way, this will go this way. Okay, so this is spreading of rays of light as they pass through air, then through a diverging lens, is called the divergence. Divergence, to diverge, means to spread far apart. Okay, so if you continue drawing these rays of light backwards, they will appear to have originated from a common point. We'll see what this point is called just in a short while. So the spreading of the rays of light after refraction. So refraction happens there, it happens here. So the spreading of the rays of light after they have been refracted is called the divergence. So we are saying a lens can cause refraction in two ways. One, by convergence, or by being converged, or being brought together, rays of light coming to a common point, or by being spread far apart. That's called divergence. To diverge means to spread far apart. To converge means to come to a common point, as in the case of convex lenses, the action of convex lenses. So you'll be asked a question to say, state the effect of a lens on a parallel rays of light. Simply say that a lens relies or depends on the principle of refraction of light. Or you can say, therefore, when parallel rays of light are directed towards the lens, the rays will be refracted either by being converged or being brought to a common point, or by being diverged. So when the convex lens is used, the rays are converged. Okay, so the rays of light are converged, meaning they come to they meet at a common point. So in this case, what we're saying is that these rays of light are parallel to each other. They're coming, let's say maybe you have lit a torch and they are beaming that torch onto a lens in front of it. So light is going to travel in straight lines from the torch, such that the rays are parallel to each other. Upon reaching the center or the lens of the lens, they are going to bend. So each ray is going to bend, except that maybe the one that passes through the center there, you call it something else in a short while. All right, so the rays are going to bend. So when they bend, they meet at a common point, which is called the point of convergence, the meeting point. So to converge means meeting at a common point. So the rays meet at a common point. Okay, we shall give this point a name just shortly. Okay, I hope we're together there. But if the lens is concave, remember concave lens is one which is thinner in the middle and thicker on the ends or on the edges. So if a concave lens is used when the rays are diverged, okay, what are we saying? We're saying if a concave lens is used, then the rays are diverged, meaning they are spread in different directions. The rays do not meet, as shown here. The parallel rays of light are beamed from somewhere, from a source. They travel in straight lines, but upon reaching the lens, they are going to spread far apart or widely apart. So in this case, this ray goes that way and this ray goes this way. Notice that the middle one, the one which passes through the center, does not get affected. Okay, now here it is seen that if you draw a dotted line like that, such that it follows in the path of the diverged ray of light, as well as down here, these diverged rays will seem to have originated from a common point there. But that is not the case. Okay? It's just a visual picture of what is going on, meaning that these dotted lines do not in practice represent real rays. Okay, we just suppose that if we draw straight lines such that these refracted rays are produced backwards, they will appear to have originated from this common point here. We shall see the significance of this point in just a short while to come. All right, I hope so far so good. So we are saying, what is the effect of a lens on parallel rays of light? The effect is that the rays of light will be refracted or bent. So once bent, they can either meet at a common point, they can converge, or they can diverge, meaning they can spread in different directions. All right, so let us look at some definitions, very critical definitions, very important definitions that relate to this topic of light and lenses. I always say that the way to unlocking the understanding of any topic lies in the understanding of the definitions, if they exist. All right, so there are some important terms which are very critical to understanding of this topic, and unless we define them now, it will be difficult for you to follow on. So we are not here to make each other's life difficult, but we try to make it easier. All right, so definitions. One of the important definitions or terms of definition of terms relating to this topic is center of curvature. Center of curvature, definition of center of curvature. All right, what is center of curvature? We define center of curvature of a lens as the center of the sphere which the lens is part, of which the lens is part. I think something is missing here. It should read the center of the sphere of which they must be off. All right, so we are saying center of curvature of a lens is the center of the sphere of which the lens is part. What do we mean? Right, let's suppose that we would like to show how a convex lens was made. Okay, so suppose I draw two spheres. Look at this as a sphere and not just a circle. A sphere, remember that a sphere is a three-dimensional shape. All right, so suppose I have a sphere like that and another sphere like this. Oh, let's see, remove this. All right, so suppose we have these two spheres. Okay, so you see that these two spheres are intersecting. In mathematics, you say intersecting. So are intersecting here. That's the intersection of these two circles. I'm still not comfortable with this circle here. So let me redraw. All right. So suppose we have these two circles or spheres such that this region here is the intersection. Okay, where the two circles are overlapping. Now, if this is the center of circle, let's say this is circle A, and this is circle B, or sphere B. So each sphere has a center like this. Okay? All right? Now, the point of intersection, or the region in which these two circles are intersecting, you can see that it basically represents what? A lens. The shaded part is like this. I've shaded it. You can see that it is representing a lens. All right? So what you call the center of curvature is the center, this is center 1 of the sphere, and this one center 2 of sphere B. So the center of curvature refers to the center of the centers of these two spheres, such that if you consider these spheres, you actually see, appreciate that their point of intersection, the region where I'm shading, this one here, represents a lens. Represents a lens. This one. All right. If you remove the rest of the parts of the sphere, you simply have a lens. You have a lens. The remaining part will represent a lens. So the center from which these spheres are drawn, which is here and over here, are called centers of curvature. Centers of curvature. You can see from this that if you look at circle A, circle A has a part of its curve shared with circle B, this one, the one I'm highlighting in green. Similarly, for sphere B, it also has this part, all right, which is a part of sphere B. So that's how we define the center of curvature. The center of curvature. Another one is the radius of curvature. We define the radius of curvature as the radius of the sphere of which the surface of the lens is part. Once again, suppose we have two spheres, call this C1A, and another one, call this one B. Right. So if I shade the intersection, here, this region here, I shade it, you see that this is forming a lens. It's forming a convex lens. So the radius which was used to draw these spheres is called the radius of curvature. So if this is our center, this is another center. Remember, radius is the distance from the center of a circle to its circumference. So in this case, this distance here, denoted by the letter R, is the radius. Similarly, this one here is another radius. So these radii are called radii of curvature. One is radius of curvature. Okay? So that's basically what we are saying. Another term which is very important is the principal axis. Definition of principal axis. We define principal axis as the line joining the centers of curvature of its surfaces. All right, so once again, if we look at the two spheres that were used to make or to construct a lens, all right, such that this is our center of curvature, so call it C1, and another center of curvature there, call it C2. This distance here, as long as it is passing through the center here of the lens, is called the principal axis. So a principal axis is simply a line joining the centers, the two centers in this case. Okay, so this line here, if it's passing through the center of the lens, is called principal axis. So put together everything, this becomes the radius of axis. This one here, also another radius of axis. Then we have C1 and C2, which are the radii or centers of curvature. So we have radius of curvature for sphere A, and the radius of curvature for sphere B, denoted by R, and the C1 and the C2 are the centers of curvature. So the distance joining C1 and C2 is called the principal axis. So if you have a lens like this, and is stripped through, this line passing through the center of the lens is called the principal axis. All right. I hope you are picking up the bits. All right. Now, another important term to consider is what is called the optic center. Optic center, denoted by O, is simply the point on the principal axis midway between the lens surfaces. So let's suppose that we have a lens. Like this, and this is the center. Okay. If we draw a line, something like a line of symmetry, this distance should be equal to this one here. So if these two distances are equal, let's say this is D1 and this is D2. Okay, suppose we have our lens. All right, so the point C, which if it's passing through the center of the lens, okay, let's denote it with the letter O. If it's passing through the center of the lens, or it's lying on the principal axis, this is principal axis, then this point is called the optical center or optical center. Okay, so it is a point on the principal axis midway between the lens surfaces. Okay, so this is the very center of the lens. This is the very center of the lens. It's called the optic center. So put simply, optic center is simply the center of the lens. The center of the lens. Another one is the principal focus. Principal focus is simply, for a convex lens, is the point on the principal axis where all rays converge after passing through the lens. What are we saying? We're saying that principal focus for a convex lens is a point on the principal axis where all rays converge after passing through the lens. But for a concave lens, it is a point on the principal axis where the lens from which the rays seem to diverge from after passing through the lens. I'll take this again. We are saying for a concave lens, it is a point on the principal axis behind the lens from which rays seem to diverge after passing through the lens. A diagram will help you to understand this. All right. Another term which is also very critical is the focal length, denoted by f, small f. So focal length is the distance between the optic center and the principal focus. Okay, so what we just said recently is that if we have this as our convex lens, and we have parallel beam of light, rays of light, such that they bend, where they meet here is called the principal focus, denoted by capital F. Principal focus. Now, the distance between the principal focus and the optic center, which is this distance here, is what is called the focal length, denoted by small f. I hope we are together there. All right. Another term is called the focal plane. We define a focal plane as the plane. A plane is just a line which is perpendicular to the principal axis. This should be perpendicular to the principal axis. I think something is missing there. That all rays seem to converge to or seem to appear to diverge from. Okay, so the incident rays in this case are not parallel to the principal axis. Okay, so let's say we have a lens, convex lens. Remember, the principal axis passes through the center O, and all other rays will diverge or bend or converge, will converge and meet at a principal focus. So the point where these meet is called principal focus. All right. So we are saying if we draw a line which is perpendicular to the principal axis, that such that rays seem to converge to or seem to appear to diverge from. So that's this region here. So this dotted line which you see is what is called the focal plane. So this is the focal plane. So over here, this line, we have the focal plane. It's passing through the point where the rays seem to meet, which is called the focal, the principal focus. The principal focus. All right. Okay. Another important term to think about is the parallaxial rays. Definition: parallaxial rays are rays that are parallel and close to the principal axis. Okay, we can show this diagrammatically. Suppose this is a lens. All right, so we have rays that are parallel to the principal axis. We have rays that are parallel to the principal axis. So all these are parallel to the principal axis. So the principal axis being this one. So ray, if you number these rays as 1, 2, 3, and 4, this being the principal axis, PA. So rays 2 and 3, 2 and 3 are parallel to the principal axis. Okay, but also they are close to the principal axis. 2 and 3 are called parallaxial rays. Parallaxial rays. Then we have what are called marginal rays. Marginal rays. These are rays that are parallel and far away from the principal axis. If I bring back that diagram, suppose this is a lens, and then we have principal axis, PA, all right, such that we have rays that are parallel to it. They're parallel to it. If I number these rays as 1, 2, 3, and 4, we said that rays 2 and 3 are close to the principal axis, therefore they are parallaxial rays. But if you look at ray number 1 and the ray number 4, they are parallel to the principal axis, yes, but they are far away from the principal axis. These are called the marginal rays. So the difference between parallaxial rays and the marginal rays is to do with the closeness to the principal axis. I hope we are together on these definitions. So we can appreciate these definitions, some of them, by looking at the diagram here we have here. So we said that the center of the lens is called the optic center. This label is for the optic center. The distance between the principal focus, which is this one, and the center of the lens is called focal length. Focal length. All right. The point where the rays meet after refraction from the lens is called the principal focus. Principal focus. The line which passes through the center of the lens is called the principal axis. Principal axis. Principal axis. So take note of these labels. Similarly here, if you have rays of light that are parallel to each other, the principal axis is drawn through the center of the lens. Okay, maybe before that, this dotted line here is the focal plane. This is the focal plane, the dotted line, but it passes through the principal focus. Similarly, the focal plane is this dotted line, and this line in black is principal axis. After refraction, these rays will meet here. This is the principal focus, the principal focus. Okay, and this dotted line here is the focal plane. Similarly, for a diverging lens, these rays of light seem to come from the same side where light is coming from, the same side of the lens. All right, so this point is called principal focus. For a concave lens, notice the principal focus is on the same side as the source of light. All right, so you have this point as the principal focus, and then you have the principal axis passing through the center of the lens, and so on and so forth. All right, so today we were just looking at the definitions of terms which are commonly used in this topic. For now, let me stop here, and once again I urge you to subscribe to the channel so that you don't miss any videos as they are uploaded. My name once again is Mr. Pochilola. Bye for now.